Okay, good morning, everyone. So last time we were talking about absorption of light. And we attacked this. So we're talking about, for example, we have some initial state. You can think of this as an atom with the electron in one of the atomic levels. And it absorbs some light with frequency omega, the energy of which is h bar omega. And then it's going to some final state. And so right now we're not being specific about what the initial and final states are, but you can think of them as states of some atom, for example. And then we used time-dependent perturbation theory in the form of Fermi's golden rule. Okay, and then we got a result. And last time at the end, I had written the result in the case where the final state is continuous. So what that means is, for example, if my initial state was some atomic state, my final state might be some unbound state, for example, where I've knocked the electron free, and now it's almost in a free state. And that would be, for example, ionization of an atom, where I knock the electron out. And in that case, what we compute is the cross-section. So Fermi's golden rule gives us a rate, but then we turn it into a cross-section. Cross-sections should always have units of area. It's the effective area for something to occur. And we did that by integrating over the final state energy, which is a lot easier than it sounds, because in Fermi's golden rule, there was a delta function for the final state energy. And so it just amounted to replacing the final state energy with the value of the frequency. And so we got a formula that looked like this. So this is a formula for absorption to go from an initial state plus a photon to a final state. And so it had various parts. First, there's a prefactor, which involves the fine structure constant and some 4s and pi's and stuff, and h bar, and the mass of the electron squared. And then it had 1 over the frequency, but now because we integrated over the final state energy, this frequency is fixed, because it's forced to be equal to the final state energy minus the initial state energy over h bar. Okay, what else was there in this formula? There was a matrix element. So this matrix element is many times going to tell you, oh, that transition can't occur because the matrix element vanishes. Those are called matrix element selection rules. Okay, and more generally, it's something you have to compute. It involves this little curly e thing is a unit vector. That's the polarization of the light. It's a vector, a unit vector. It's just telling you what direction the electric field in the light is pointing. So this is unit vector perpendicular to the direction of propagation, which we're calling k hat, and it's along the electric field direction of the wave. Then the other thing in that matrix element is an operator that we identified last time, and it's e to the I k dot r. R is the position operator times the momentum operator minus I k cross the spin. So all of those are operators that act on the initial state of the atomic system. Okay, so we compute that matrix element and we have to square it. Then we have to multiply by a density of states, which includes the possible effects of degeneracies of energy. So this factor here is density of states. And this thing is the degeneracy. So we've summed over all the energies, or integrated over all the energies. But for each energy, maybe there are 3 different atomic levels, or 3 different spin states for the final state. In fact, for electrons, there typically will be, because the electron, if I've ejected an electron from the atom, it's got 2 possible spin states. So I would have to sum over those as a degeneracy. Okay, so all of that was if F was continuous, but now you could say, okay, what if the final state is discrete? Which doesn't mean it's careful, it means it comes in different levels that are separated from each other. And so unlike what I just said, this would be, for example, bound states. So this would be what you would compute, for example, for atomic transitions. For example, if I start in the ground state of an atom and I go to the first excited state, that's a discrete state. And so I would use the formula that I'm about to write down. So in this case, it's more likely that instead of computing the cross-section, you're just going to compute a rate directly. Okay, and when you compute that rate, you can't integrate over the final state energy, because the final state energy is some discrete thing. But you can still make use of the delta function that comes from Fermi's golden rule by instead, now what we're doing is we're going to integrate over the frequency. So implicit in that is that we're assuming that there is light of lots of different frequencies present. And so we're just going to be integrating over all those frequencies. And so really, to write down the answer, we need to specify how much light there is with a given frequency. Okay, and so let me just write down the answer, which is justified in the notes in more detail, but we'll write it down in a way that hopefully at least makes it plausible. Oops, still doing absorption. So I have initial state plus h bar omega goes to a final state. But now it's going to be proportional to the intensity of the light. So I'm going to write down a factor I of omega and tell you what it is in a minute. But then the other factors here look like this. So there's the usual fine structure constant. There's the same matrix element squared. That's not, the form of that at least isn't going to change. So I'm just going to write it schematically. And now let me tell you what that I of omega is. This is the intensity of light per unit frequency. Which is otherwise known, what's intensity? That's power per unit area. Per unit frequency. Okay, so this is just telling you how much light do you have in each little bit of frequency that you integrated over. And to relate it to Fermi's golden rule, this is equal to the density of states times a factor that's telling you how much energy each state has, or how much power each state has. Okay, so rho of omega, the density of states, that's how many states you have with a given frequency. And this other factor here is energy per unit time, otherwise known as power per unit area. Okay, and now if I sum over all the states, which we're supposed to do, multiplied by those factors, that's the intensity per unit frequency. So just to normalize things, the total intensity of the light is equal to just the integral of this I thing with respect to frequency. But the total intensity of the light isn't what matters. What matters is specifically how much light do you have to have the right frequency to match the initial and final states. Okay, so that's the omega that actually appears here. Again, this is final energy minus initial energy over h bar. Okay, so to know how often the transition occurs, you need to know the intensity of light with that amount of frequency. Now, there's another way to describe this, which is equivalent and is going to be very useful for what we're going to do later today. And that is, instead of describing it in terms of intensity, you can describe it in terms of the number of photons present. So can describe in terms of photon occupation numbers. Okay, and so the idea behind that is consider photons that have each possible value of the wave number, which is the propagate or the wave vector, which is the propagation direction times omega over c. That's from the classical mechanics of electromagnetic waves. And the other thing you have to know about a photon to know everything there is to know about it is its polarization. What direction its electric field is pointing. Okay, so here's my propagation direction, and classically, I have an electric field that's doing that. It's oscillating up and down. This direction is k hat, and this direction of the electric field is my polarization vector. But I can have as many photons as I want in that mode. And so let's let the number of photons let's call that capital E, and I have labels for it to tell me what my direction of propagation and my polarization are. Okay, and each photon has a known amount of energy, namely h bar omega. Okay, so now it's a little bit of a problem to translate the knowledge of how many photons do you have in a given mode, how much energy do they have, and convert that into the intensity. And I'm not going to go through the details, which are in the notes, because it's kind of tedious, but I'll just write down the answer here. The intensity is equal to and can be replaced by some numerical factor, which happens to go like the frequency cubed over 8 pi cubed c squared. And then I need to integrate over all possible directions that the photons could be going. Okay, so a reminder, whenever I write d omega, that's really integrate over the angle, but now the angles I'm integrating over are the angles that the photon could be moving in, like so. And then I need to sum over all the possible polarizations. But when I do this sum, these are perpendicular to k hat. And then what I'm summing over is the photon occupation number. Okay, so hopefully it should at least be plausible that if I increase the number of photons, I'm going to increase the intensity proportional. And so the details of how you get those numerical factors are in the notes. Okay, it's basically just looking at the classical mechanics of electromagnetic waves. Okay, so that's going to be useful in a little bit, the fact that we can translate the rate, basically, so the rate for absorption, as you might expect, is proportional to how many photons there are to absorb. If there are more photons to absorb, the rate will go up, proportional to the intensity, which is indeed appearing in the formula. This is the rate for it to happen. Okay, but now let's turn from absorption to emission of light. So the good news is that we've already done or already seen all the difficult math that we have to do. It's going to be the same math. And the reason is because when we did Fermi's golden rule for a harmonic perturbation, there were two terms and they looked almost identical. In fact, what were the differences? That one difference is there was a different delta function. So instead of this delta function, which occurs for absorption, we're just going to get a delta function that looks like this. And all that's saying is that for absorption, my final state energy has to be bigger than my initial state energy by h bar omega. But if I'm emitting the light, then my final state energy should be less than the initial state energy by h bar omega. So that was one ingredient that changed in Fermi's golden rule between absorption and emission. And the only other thing that changed is instead of my taking matrix element of my perturbation V, you take matrix elements of V dagger, which in our case means, remember the matrix elements are matrix elements of this operator curly P, which is a vector. And so that's going to be replaced by its dagger. And the other thing that went into the matrix element is the polarization of the light, which will be replaced by its complex conjugate. So many times that makes no difference whatsoever. For example, I can always choose my polarizations to be just real unit vectors, and then taking the complex conjugate of it does nothing. But I could also maybe choose circularly polarized light, and that occurs sometimes. And then circularly polarized light has complex polarization vectors. So in that case, I would just have to remember to take that complex conjugate. Okay, so that means we don't have to think much. We can just take what we had before for absorption and write down the formula for what's called induced emission. This is for an initial state going to a final state plus h bar omega. Okay, and so what is it going to be? It's going to be our intensity, which we also know from right up here that we could, or we can if we want to, write as a big sum over all the photon occupation numbers, how many photons there are in each mode. Okay, and then there's the same factor for pi squared fine structure constant, mass of the electron squared, h bar omega squared. And then I just have to write down my matrix element of the Hermitian conjugate operator that I wrote down for absorption, but otherwise it's the same. Okay, and that's the case for discrete final states. So discrete final states is probably almost always what you want to use, because if you're emitting the light, that means the final state is lower in energy than the state you started with. And so it's very likely to be a bound state. For example, I could compute this, and probably we will in the future compute this rate when I'm, say, going from the n=2 state of the hydrogen atom to the n=1 state. So the final state's going to be very likely a bound state, and therefore a discrete state. Okay, so a picture of what's going on here is, let me just draw a circle and say my circle here represents an atom in an excited state. Okay, and then the thing that I'm computing here depends on how many photons there are present. And in fact, it's proportional to the number of photons that are present. If I go back to my formula for I, it's proportional to that number. So the picture I have here is I've got this atom, and then I have, let's say, n photons coming along to hit it. And really, I should tell you how many photons there are in each mode, but I'm just saying n here. And so this is the before picture. And then the after picture is I have my atom in a lower state. Okay, but now I've emitted an extra photon, and so I've got n plus 1 photons coming out of here. And so that's what this is the after state. That's what we've computed the rate for. Okay, and so that's why we say this transition is induced by the light. If there was no light there to begin with, then the thing we computed would be 0. And so just for the record, let's write down the answer in terms of the photon occupation number. So what do I do to do that? I go back up to this formula. I plug that in. I cancel whatever pi's and h bars need to be canceled. And you get this. You get fine structure constant, omega over 2 pi mass of the electron squared, c squared. And now I have to integrate over all the possible directions for all the possible photons that might be present, sum over all their polarizations, multiply by the number of them with each of those properties. Oops, I got that backwards. This should be K and polarization hat, and with the appropriate matrix element. Which looks like that, and it's squared. Okay, so that's good so far, but so let me just write down this fact. The rate that we've computed to emit a photon is proportional to the number of photons already present. But that might seem kind of weird because let's say I have an atom in an n equals 2 state of hydrogen and it wants to decay to the lower state. That's allowed by energy, so why shouldn't it be allowed to do that? And the answer is it can't. It's just that the calculation we've done doesn't show that. And so the calculation we've done isn't quite exactly right. So you can say, what if there are no photons already present? Then you can still have emission of light, but it's called spontaneous emission. So we'll write spontaneous here. Okay, and the reason our calculation doesn't show that is because we've been treating the electromagnetic field as classical and then promoting the things into operators. But really, electromagnetic fields are quantum systems themselves. And to get the answer for spontaneous emission, the best way to do it is to take that into account. Okay, so I'll just write down here our calculation doesn't show this. We need to see it directly, we need to quantize the electromagnetic field. So we're not going to do that in this course, not because it isn't a great subject and fascinating and worthwhile doing, but just because we don't have time to go off in that direction. But we're still going to be able to write down the answer, and we're going to write down the answer due to the way it was originally found before people understood how to quantize the electromagnetic field. And so this is an indirect argument due to Einstein. So it's very indirect, and yet it's going to give us the right answer. And this is known as his A and B coefficients method. And it relies on, of all things, statistical mechanics. Okay, so just to say what the goal is before we launch into it, our goal is to find the rate of spontaneous emission for an initial state going to a final state plus h bar omega from the calculation that we've already done, which is the induced emission. And so what we're going to find out in the end is that they're simply related, even though it might not seem that way along the ways. Okay, so let's see how this argument works. So what we're going to do is consider a very simple situation where we have some cavity whose walls are magically made out of just the two states that we're interested in. So walls are made out of, let's say, atoms in two states. We'll call them A and B. The reason we're not calling them initial and final is because these states will both play the role of initial and final in the argument we're about to do. But we're going to assume that one of the states is higher in energy. The B state is going to be in higher energy than the A state by an amount that we're going to call h bar omega. And that means the state B can transition to the state A by giving off a photon, and A can transition to B by absorbing a photon. Okay, and now we're going to assume that everything, the whole system we're doing, is going to be kept at some temperature. It doesn't actually matter too much what the temperature is, but what's important is that we can change the temperature, but we're going to keep it constant at any given moment. So it's kept at temperature T with electromagnetic radiation inside the cavity. Okay, so here's a cartoon picture of what's going on. We've made ourselves a cubic box. On the walls of the box are a bunch of atoms, and they are all in states A or B. Maybe like that. And you're always more likely to have state A because it's lower in energy. Okay, and then buzzing around in the box between atoms are a bunch of photons, like so. And this is supposed to be an equilibrium because we've kept the temperature constant. And so all the time you're having transitions going on that are A plus h bar omega goes to B, and B goes to A plus h bar omega. Okay, now here's where the statistical mechanics is going to help us, is that what statistical mechanics tells us is how many things there are in each of the states, the relative number of them. It won't tell us the absolute number, but we're not going to need that. Okay, so the relative number
I'm sorry, Professor.
of A and B states. Yes, go ahead.
Can you please explain this example again?
Sorry, which part of it?
I kind of fell behind from the part you started the animation. Could you please explain it again?
Okay, so we've got this cavity. The walls of the cavity are made out of atoms, which we're going to assume are in two possible states, A and B. Okay, and then we heat it up to some temperature. It's not going to turn out to matter what temperature we heat it up to, but we're keeping it at equilibrium at that temperature. And then there are photons that are being emitted and absorbed. And because we have equilibrium, we are assuming that these transitions are occurring between A and B states by emitting and absorbing photons according to the fact that their energy is different by an amount h bar omega.
So what is exactly meant by an atom being in a particular state? I don't understand that.
So quantum systems come in states. And so we're just saying that an atom can be in one state or another. Right? So we calculated, for example, in the hydrogen atom, we calculated all the possible energy states, the bound states of the hydrogen atom last semester. And we're just saying that you're in the atom can be in any one of those states.
So like, for example, when you had electrons, you mentioned they can be in ground state or excited state. What does it mean for an atom to be in a particular state?
So in an atom being in a state just means, I'm not sure how to explain that any different way. Quantum systems, that's one of the postulates of quantum mechanics. Quantum systems are in states. And so a hydrogen atom can be in an n equals 1 state or the various n equals 2 states. I'm not sure how to answer it in a different way.
Okay, thank you.
Okay. So the relative number of A and B states is dictated by statistical mechanics. And statistical mechanics tells us there's a Boltzmann factor, which says the relative number of atoms in the energy level A is given by the exponential of minus its energy over the Boltzmann constant times the temperature. Okay, and for the B states, it's the same thing except with its energy. But not only that, there's the net relative number of states with n photons. And so we're going to be using all three of these factors. The one with n photons is e to the minus n h bar omega. That's the energy of a state with n photons, divided by Boltzmann constant times the temperature. So this is the Boltzmann hypothesis for statistical mechanics, is you want to know the relative number of things in any given state, you compute that Boltzmann factor, and that gives you that relative number. Okay, so the first thing we're going to do with that Boltzmann factor information is for a given photon mode. So we're just going to imagine that we're fixing the frequency and the polarization, and we're going to calculate the average number of photons in it. Okay, and I'm going to write that average number as n with a bar over it. That means average. Okay, for a given direction and polarization. And so what do? We don't know the absolute number in each mode, because, for example, that would depend on the volume of the box. If I make the box bigger, I might get more. Okay, but I can take a sum over every mode. The that I would have in that mode multiplied by the Boltzmann factor. Okay, and then to normalize it and get the average, I have to do the same state. They have to do the same sum. Okay, that's just dividing by the normalization to get how many there are. And the great thing about that infinite sum is you can do it exactly. It's a geometric series. And the answer looks like that. Okay, so if you know the temperature and you know the frequency of the photon, you know how many photons there are present in that state. So that's a really powerful fact. We're going to use that in a little bit. I'm going to call it, therefore, fact 1. So I will refer back to fact 1 after we do a little bit more of talking about the atoms in this box. Okay. So the next thing we're going to do is we're going to talk about the fact that we're in equilibrium. Equilibrium. So what does equilibrium mean? Equilibrium means the number of the number of photons in each state isn't changing. So I can write 0 is the rate of change of the number of photons. I'm going to leave off the subscripts because they get tedious to write. But now if I think about it, what are all the different ways the number of photons could be changing? So there's one place that they could be changing, and that's spontaneous emission. And another way that they could be changing, that's the thing we want to know. And then there are the other things that it could change the number of photons. There's induced emission. And then the third thing that could change the number of photons is absorption. And all of these things are going on at the same time because the atoms can emit or absorb photons. But now let's write down what we know about each one of these. We know a little something about each one of them. So for example, we know the rate of change.
Sorry, Professor.
Of spontaneous emission. Sorry, go ahead.
Thank you.
So the rate of change of spontaneous emission is, so one thing that it's true is it's proportional to how many atoms you have present to emit something. And that number of atoms is n sub b, the number of atoms present in state B, right? Because if I have twice as many atoms available to emit photons, I'll get twice as many of them emitted in a given amount of time. And so it's proportional to that, and we'll just call the constant of proportionality A. I think Einstein actually had it normalized a little bit differently, but we're going to call it A. It's the same idea as his A. Okay, and then similarly for induced emission, okay, that's proportional to the number of atoms present. But because it's induced, by definition, it's also proportional to the average number of photons present. And then we're going to call the constant of proportionality B sub BA. It's just a name that we're giving to the constant of proportionality because we know it's proportional to n sub B and we know it's proportional to n. And then thirdly, we know that the absorption rate, so really what this is telling us is how do the number of photons change when I absorb photons? So first of all, it's negative. If I'm absorbing photons, I'm reducing n as time goes on. It's proportional to how many photons there are present, n bar. And it's proportional to how many atoms there are that are available to absorb photons. So that's what we're going to call n sub A. Okay, and then the constant of proportionality we're going to call B AB, meaning it's something that depends on A going to B, whereas this was something that depended on B goes to A. Okay, so just a comment on these things. These constants of proportionality are, of course, proportional to the rate for a given atom to do something. So for example, A is proportional to the spontaneous rate for B goes to A plus H bar omega. B sub BA is proportional to the induced emission rate for B goes to A plus H bar omega. But there's something very important here, which is notice that when we wrote down our constant of proportionality, we already factored out the number of photons, which was, when we computed this thing, present in the formula. So to account for that, I have to divide by n. Okay, and then similarly for BAB, that's proportional to the absorption rate. But when we computed that, that had a factor of n. But notice right here, I've already included the n that it's proportional to. So here I need to write divided by n. Okay, now what else do we know? We know the Boltzmann factor distribution that I wrote down before. That doesn't tell us how many atoms there are in each state, because again, that would be proportional to how big I made my box. But it does tell me the ratio. So the ratio of the number in state A to the number in state B is equal to e to the minus Boltzmann factors divided by k Boltzmann times time. Okay, and by definition, I claim I know what the energies of those are. So there's an h bar omega factor that goes there. Okay, and now we finally have enough to solve for the average number of photons. And so specifically what we're going to do is we're going to take this equation and this equation and this equation and this equation and that equation, and we're going to solve for n bar. It turns out, if you stare at it long enough, you'll realize that's enough equations, because here this is equal to 0. That's enough equations to solve for n bar. Okay, and so I'm going to call this fact number 2. Okay, is that n bar is equal to, when you solve those equations, the A coefficient divided by the BAB coefficient, e to the h bar omega k Boltzmann times temperature minus B sub BA. Okay, so that's fact number 2. And now let me remind you what fact number 1 was. Fact number 1 said that n bar is also equal to this, which looks very similar. So now for both of these things to be true at the same time, if you stare at it, you'll realize there's only one way that can happen. Because in the numerator, in both cases, I have constants. In the denominator, I have a negative constant, and I have an e to the h bar omega Boltzmann factor. And so if I imagine doing this experiment many times with many different temperatures, the only possibility is that this constant ratio to that has to be 1, so that this dependence on temperature can match with that dependence on temperature in the denominator. Okay, and so in equilibrium, this is true in equilibrium. But that means we must have A equals BAB equals BBA. There's no other way that these two formulas can match unless those things are all equal. So I don't know what they are individually, but I know they're all equal. When Einstein originally did this, he had it normalized differently, so there were some extra factors. I've redone the argument just by changing the normalizations of the A's and B's so that they're all equal in the end. Okay, now what does this have to do with the calculation we've already done? So it turns out we already knew this fact. We knew that BAB is BBA because we computed it last time as the detailed balance. So we already had BAB equals BBA. That was detailed balance from last time. Okay, and that just came about from the fact that we calculated the absorption and emission rate for induced emission and absorption. And we found there was this relation between them that would involve the density of states. Here, everything's really easy because we only have two states that we're talking about. And we're just making things easy because we're not worried about degeneracies or anything like that. And so the density of state factors in the detailed balance formula just doesn't even enter in. And so that just means that the rates are equal. So that is good. That's showing us that statistical mechanics is in agreement with the calculation we already did. But now we get a new fact. This is Einstein's idea. Since A is equal to BAB, if we think about how does that translate here, that means that the spontaneous emission rate for B goes to A plus H bar omega has to be the induced rate, the thing we actually calculated, for B goes to A plus H bar omega, except that we have to divide by the number of photons present in each mode. Okay, so that's the only way this can be consistent with statistical mechanics. That's the argument. So in other words, the induced rate that we actually calculated had this factor of n in it, the number of photons. And now what Einstein's method is telling us is that if we want the total of induced plus spontaneous, we need to include the induced part, and then the spontaneous part is just adding 1 to that. So what that means is the rate for spontaneous emission, even though we couldn't calculate it directly, we now know what it is. It's the same formula that we had before, except now we're going to leave off the factor of n, and that will be the right answer. So this is, for example, alpha omega over 2 pi me squared c squared. This is in the version where we're writing it in terms of the photon occupation number, except effectively for spontaneous emission, the photon occupation number is just 1. Okay, so I have my matrix element that we haven't worried about computing yet. I have to square that. I have to sum over the polarization. I have to sum over the directions. Okay, but that's the formula that comes from Einstein's method. So you can get the same answer. We're not going to do it. By quantizing the electromagnetic field and dealing with it that way. And so it's very nice that it's consistent with Einstein's solution to the same problem, which is very indirect. All right, so that is going to be it for today. Next time, what we're going to do is we're going to start working our way towards applying this to actual problems, which means really we need to worry about how are we going to compute this matrix element. And so in practice, what happens is we're going to make an approximation because otherwise the matrix element's really difficult. The first approximation we're going to make is called the electric dipole approximation. And that will give us a really nice formula that we can use, especially to calculate the rate or the lifetime for atoms in excited states. We'll be able to calculate how often does an excited state decay to a lower state by emitting a photon. All right, so that will be next time. Are there any questions on today's lecture?
There's some questions from previous material.
Okay. If it's going to be on previous material, let me stop the recording here.